Welcome everyone. So today we will continue where we stopped last time, as usual. So just a recollection. So there was this relatively lengthy and not that maybe enlightening definition that the Courant algebroid, which we finally defined, is this bunch of structures. So here I'm just writing what we wrote the other day. So it's a vector bundle essentially with a bracket pairing and a vector bundle map called the anchor. And there are a bunch of conditions which essentially just these first three guys kind of tell you that everything that is with all sorts of compatibility conditions are satisfied. And the last one tells you that although the bracket is not in general anti-symmetric, the symmetric part of it is controlled by the pairing, by this operator D, which is just the composition of D and the transpose of the anchor. When recall that we are identifying E with E star throughout. And as you see, the definition is not like that short, but we will. One of the goals which we should achieve, not maybe in a couple of weeks, is that kind of there is a more conceptual way to see what this thing is, which essentially shortens the definition to half a line. Yes, we may ask why I didn't introduce it that way, and I don't have an answer for that. Okay, the main example, the motivational one, or I mean, this is how it started actually. This is like the story. Historically, people came up with this. And the main example is this guy where you take the direct sum of tangent cotangent bundle, and the pairing and anchor are the obvious ones, and the bracket takes this strange form. And one lemma which we managed to prove in the end of last time was that there is a couple of more compatibility conditions, namely like you can ask whether the anchor preserves the bracket, and it turns out that yes, that's the consequence of the first two guys. Also, as was pointed out by Philip the other day, you can actually shorten this. You can throw out one of the axioms, but so you can make it even shorter. But I won't focus on that too much because, as I said, there will be a one-line or half-line definition later. Okay, so let's start with something that's rather basic, but I find it kind of fun and useful to know in general. So let's call it. Let's not call it observation. So there is a notion of an annihilator of a vector subspace, which you probably know, but let's define it. So if V, that's what the definition is, I guess. If V is a vector space, and a subspace, then we define the annihilator, and I will call it V with the circle. That's the annihilator of V. Not V, U, sorry. This is defined to be the set of all covectors of psi in dual, which are 0 evaluated on U. So which if the whole U is equal to 0. Okay, so this is the subspace of V star. And it's not difficult to see that the dimension of the annihilator is precisely complementary to the dimension of U. So together they give you the dimension of the whole space. Okay, nothing too fancy. Now, maybe. Okay, so, and the definition. So now, if V has an inner product, then there is a similar object, and again, U is a subspace. Then again, there is a way to create something that has complementary dimension, namely by taking the orthogonal complement. Right? So we have orthogonal complement, which is a subspace of the original guy. Right? That's kind of the difference with respect to the annihilator. Okay, so this also has complementary dimension. Now, how are the two related? Well, I mean, one is a subspace of V, and the other one is a subspace of V star. Oh, it's okay, so it's probably not even worth to call it a lemma. Is that under the identification of V with its dual using the bracket, so if you take the pairing, so the pairing induces an isomorphism between V and its dual. Recall everything is finite dimensional here. So under this identification, V perp, or U perp, maps precisely to the annihilator. Okay. So this is how the two notions are related. So because for us we will always be identifying the Courant algebra with its dual, and for us there is no difference. But I can multiply like this. But okay, this is very easy to prove easy. Exercise if you want. It's a bit silly because it's just linear algebra, but it's also useful to maybe at least take this. Okay, now why am I talking about this? Okay, yeah, so let's do this. Okay. Now lemma, which is marginally more interesting than this one, it says that if phi is a vector, is a map of vector spaces, it's a linear map of vector spaces, then taking the kernel phi and then the annihilator of that is literally the same as taking the image of the transpose map. Okay, so this is essentially why I introduced that thing. So this lemma doesn't use any inner product. Okay, so this is just true for any vector space, and it's when you end up proving some linear algebraic statements, then and you want to do it abstractly without picking a basis. This is often very useful to kind of remember that there is this relation, because it kind of, at least in the area where I'm working, this pops up very often. Okay, so is the statement clear? So if I have, right, so let's prove it then. Let's say this goes between V and V prime, V and V prime, yeah? This is phi. So I'm saying that if I take the kernel, which lives here, and I take the annihilator of that, which lives in the dual of V star, okay, so annihilator lives in here, and that subspace is precisely the image of the opposite map, of the dual map. So any linear algebra uses a dual map, and the image of that is precisely the annihilator. Okay, so how do we prove that? So first let's prove this inclusion. Okay, so I want to show that if something is in the image, then it annihilates the kernel. Okay, so let's say take psi in here, V prime star. Okay, and I'm asking now if I take okay, so if I take the dual map and I hit this guy, so let's go psi prime because it's not prime. Okay, so I have an element of this, which means that I have a guy like this, and I'm asking, is this thing inside the annihilator kernel? Now, what does that mean? It means that if I apply this on the kernel, then I should get 0. Now, how this application works, if you have a dual map, it essentially tells you that you are applying this on the argument. And so, yeah, but sorry, without the star. But now, precisely by definition, kernel of anything in kernel of phi, if I evaluate it on phi, it's 0. So this is 0, hence the whole thing is 0, hence right hand side is subset of the left hand side. Good. So now Now, to show the opposite implication, it actually, because these are finite dimensional stuff, it suffices to show that the dimensions are the same. So let's calculate the dimensions. This is the first step, and the second step, calculate the dimension, and check that they are the same. So what is the dimension of kernel phi annihilator? Well, it's the, as was mentioned over there, it's the dimension of the whole space. So kernel phi is in here. This is dimension V minus dimension of the kernel phi. Okay. And now, if you what is this called? First isomorphism theorem or second isomorphism? Whatever. This thing is precisely the dimension of the image of phi. Right? Is it called like that? First? Okay, thank you. Yeah, so if you have a linear map, then yeah, the amount, the difference between the whole thing and the kernel is precisely of the size of the image. But now, famously, if you have a linear map, then well, yeah. So this is the same as the image of the dual map. And this is because if you have, for instance, if you think of what matrix is, then the rank of a matrix is the same as the rank of the transpose matrix. And the rank is essentially the dimension of the image. So, okay, so this shows that they have the same dimension and hence it's the same thing. Very easy, but very useful fact. Okay, now let's go back to Courant algebroids. So we showed if you have that such axiom, then there is this statement. Now let's show another statement, another consequence of the axioms. So for any Courant algebroid, row followed row star is 0. Okay. So what does this mean? Row is something that goes from Tm into row star maybe. So row is something that goes from E to Tm, and row star is an arrow that goes from T star, from the dual of the right side to the dual of the left side, but this space is the same because we are using the identification by the inner product. And so this thing that if you compose this, you get 0. Now this has a cute proof. So if you look at, let me give you some numbers. 1, 2, 3, 4. So essentially what I want to do is I want to take the fourth one and I want to apply this on it. I apply the lemma on the fourth. Maybe let me just write it. No need for the numbering. Okay, so take uv plus du equals d of uv, and then now hit it with an apply anchor on both sides. Okay, so what do you get on the left? Using the lemma, this thing is simply the commutator of vector fields plus the commutator of vector fields in the opposite order. But if the commutator of vector fields is antisymmetric, this is 0. Okay, so this expression is not 0, but if you apply row onto it, it's always 0 because you're mapping it to something that whose bracket is really antisymmetric. Okay, and so what is the right hand side here? I write it fully. It's row followed by row star followed by d of something. Because that's the meaning of curly d. And so we are saying that this is 0 for whatever for any u and v. So this holds for any u and v. But now this thing here, this is a composition of two vector bundle maps. So this thing implies that composition has to be 0, simply because exact forms are, I mean, any form can be written as exact forms times some functions, maybe some of such things, and you can always take the functions out of this because this is a vector bundle map. Okay, so, or in other words, you can at any point you can create any vector from something like this, any covector, and this is a point-wise thing. Okay, so anyway, this is a vector bundle map, and hence this has to vanish. It's enough to show it on the exact forms. That's the end. Okay, now there is a couple of equivalent ways to say this, which are maybe equivalent. One way is to say that if you put all these things together, then you get a short exact sequence. So if you take, I'm just writing that in the block. Sorry, not short exact sequence, complex, sorry. This thing with row and row star is a complex. Okay, because condition for being a complex is here just boils down to that one statement. Okay, that statement, that's one way. Second thing, which is actually equivalent to, which is also equivalent to the whole thing, says that kernel of the anchor map is coisotropic. That's the same as this statement or that statement. And the reason for that is, if you remember what coisotropy meant that if you take the perf of this thing, then this thing should be contained within itself. But what is this? This is simply, because we are identifying E with a star, this is simply annihilator, row annihilator, and by the statements, by this general statement, this is the same as the image of the dual. And so the fact that this thing lies, so again, coisotropy is a statement that this space is inside kernel of phi. And you see that this statement is literally the same as this one. The image of row star is in kernel of row. Yeah. Okay, so it's equivalent. All these three things are equivalent. But I mean, they're also true, so equivalence doesn't really. Yeah.
So, and the surjectivity of row followed somehow.
No, it's not. It's not surjective.
Also, then it is not.
It's not. It's not.
It's not exact.
It's not. Sorry, it's not exact. I messed up, but yeah, no, it's just a complex.
It's complex. You didn't say.
Yeah, exactly. It's not.
It's not exact.
It's not exact.
But you never said that, so it's fine.
I said it's a short exact sequence, but it's not. Sorry, it's not.
So it's not short, then it's not exact. So.
Exactly. It's just a complex. I was kind of.
It's a short.
Sure.
It is short still, yes.
It's not short. It's long.
So now, with this in mind, then we can define. Let's call this somehow. Let's call this complex. Like this. So now, famously, so there is some interesting process in Courant algebroid. So Courant algebroid, I will shorten the CA. I guess by now we know that it's Courant algebroid. I mean, I shortened it as well. So this thing is called exact if that sequence is exact. It's called transitive if row is surjective. Okay? In other words, this sequence is exact at this point. And even more generally, it's called regular if the row has constant rank. I guess image of row. That's constant rank. space of Courant algebroids. Inside it we have regular ones. Inside that we have transitive ones. And inside that we have exact. It's a Venn diagram of sorts.
And your lemma kind of, but if row is surjective, then row star is injective in binary dimensional.
Yes, that's exactly, yeah. I will mention that in a second. But yeah, very good. So yeah, in fact, okay. But let me write a statement, and then you can think about how to prove it, and I will erase the board in the meantime. Put it here. Proposition. Lemma again. A Courant algebroid is exact if and only if it is surjective. Sorry, if it's transitive and some simple dimensionality broke. So dimension of 2 times dimension of m is precisely the rank. So you can think about that while I erase the board. So one part is, as was mentioned by Kamash just now, it's used in the proof. Where is this one? Okay, any ideas about the proof? Actually, I can write it there.
Convention is clear.
Hmm?
The condition on the dimension is clear.
Right. So I realized that I erased the sequence, but okay. Let me write it here again. Yeah. So let's say that we do it at a point, because this is a sequence of vector bundle maps, so we can just do them at a point. In which case, this is just a map of vector spaces. This is row and this is row star. Now, exact. Well, what's the cleanest way to say this? Well, okay, yeah, let's say like this. If you have a map of vector spaces, so this is exact. If and only if this would be some general, let's say I have A, B, C, 0, 0, and let's call them somehow chi and omega maybe. So this is a vector space. So if I have a sequence of linear maps of vector spaces, then this is exactly even only if I have exactness at 3 places. So this image of so omega is surjective, chi is injective, and because these are vector spaces, then the exactness in here is it can be just very down to dimension counting. So dimension of B is the sum of dimension of A and dimension of C. If you want, no, there is various ways to see this. You can also use the lemma from before to check this. But okay, so yeah, and so for us the exactness would mean okay, so we would need this thing to be surjective, this thing to be injective, but as Tomasz pointed out, these are equivalent. So rho is surjective if and only if its dual is injective. That's again something that you can check with that lemma. Let's check that. It's fun. Okay, it's a simple statement. So what does injectivity mean? Injectivity means that I take surjectivity of rho. Surjectivity means that I take the image. So rho star injective is the same thing as kernel of that map being 0, which is the same thing as saying that the annihilator of the kernel is everything. It's the whole space. In this case, rho star goes from to E. Okay, so this is the same as dimension of E, right? Am I going in circles? No, because okay, so this thing is the annihilator of kernel. So this is the same as image of the dual map. In this case, their dual map to rho star is just rho. So image of rho equals dimension. This is not dimensions, but the spaces. So here I use the lemma from before. So this is the image of rho, and image of rho being E is the same as rho being surjective. Okay, so this is just to show that. So okay, so the statement here, we see that exactness of this whole thing is actually the same as exactness here and here, because exactness here is equivalent to exactness there, and the exactness in the middle is just the dimension count, and that gives you this one, because these guys have ranks the same as the dimension of n. Okay, so this was some. Well, yeah. So if you want to check that the Courant algebra is exact, then you know it's if I give you some abstract one, then one way to check if it's exact, it's you need to check that rho is surjective and that some dimensions work. Because there, maybe it's not clear now, but there. Oh, I won't jump. Okay. So that concludes this kind of basic consequences of the definition part. So let's do the classification business, which is the first non-trivial theorems, maybe, where non-trivial theorems appear. Classification. Okay, any questions before that?
So, like the real world interesting Courant algebroids, to which class did
Very good. Actually, I wrote that down in my notes and I forgot to say. So remember, let me do it again. So there is this. Let me ignore regular because okay. No, let me write it. So Courant algebroid, regular, transitive, and exact. And well, depending on what you mean by real world application, if you mean applications to supergravity, for instance, or string theory more generally, then this bubble here is related to heterotic or type 1 string. In particular, I mean, there is a little bit more because we will get there. I hope to get there today, actually. Not here, but like to see at least maybe progress classification business. But these ones are related to kind of the more standard bosonic string or type 2. I mean, this is more of a propaganda or advertisement. It's not really like. I'm just saying that these things are related to that. And maybe you might see later on a little bit how. So that's the relation to string theory. Apart from that, you can relate it to. Well, there is other interesting things to it. I mean, Courant algebroids are related to Chern-Simons theory. That will be still the transitive case. And but you can get some topological field theories for the completely general algebroids.
So what about the class of regular ones? I haven't seen much about like.
Yeah, me neither. Yeah, I don't have too much to say about that. I don't have much to say about that. I just included it because I don't know, to make them more circle. But I mean, I mostly, personally, I move typically within transitive. If I do examples, then it's usually that one. But there is some interesting. I mean, maybe not in this context, but I kind of even seen, not in the Courant algebra context, but it's like some sort of neighboring type of algebroids, and there I think you might get something interesting even outside of the regular case. But let's not talk about that. Okay, so now first let's take it as a proposition. So let M be a manifold. And H an arbitrary free form. Then the following structure. Take it to P plus T star. I'm essentially copying that. I didn't figure out a better presentation than I will just copy it. This one, that anchor map, and with a bracket which looks like that one, but then it continues. So then this thing is a Courant algebroid. If and only if H is closed. Okay, so I'm essentially saying that you can take this example and you just add one more term here, which takes two vectors and produces a conform. And I'm saying that satisfies the axioms if and only if H is closed. Okay, okay, so I'm not going to bore you with the calculation, but I will show you kind of the most interesting bit. So let's say I show you this implication to at least see why this needs to be closed. Then all that remains is to check that everything else holds. And the easiest way I found is actually to do it in indices, because that's kind of the shorter one. So let's say I want to calculate. I want to calculate this first axiom for this expression for coordinate vector fields. So you take partial I, partial J, partial K, and I put it on one side. So partial I, partial J, partial K. It becomes coordinate vector fields. If you like, you can do it for arbitrary vector fields, but then you have to play a little bit with the Cartan calculus, which is fun, but it's kind of it's twice as long as doing it this way, actually, 3 times maybe. So I'm a man of efficiency, so I'm going to do it this way. Yeah. So the Courant algebroid axiom states that this is 0 by default. If E is a Courant algebroid, this thing is 0. So I just calculate what it is from this formula. So okay, so what is this, for instance? So, well, if I only have two vector fields, x and y, I only get the commutator, the lead derivative, and this last term. But because they commute, then lead derivative of partial j of partial k is 0, so this thing just doesn't contribute. That's the reason why I picked the fundamental, the coordinate vector fields. So, but this thing contributes. So this thing is actually h, j, k, l, dxl. Okay, if I use this dual basis, and you get the same thing here. This thing here is h, I, j, l, dxl, and same here. H, I, k, l, dxl. Okay, so now if I continue, then I have now a vector and one form. So x, beta. So there is only one term. So this is the lead derivative of this. Let me write it. This is the lead derivative of partial I with respect to partial I of this guy. jkl dxl. Note that the last term is literally the same as the first term, except I swapped I and j. Okay, this thing and that thing, they look the same. I can put minus and I directly write the other direction. So this is the third term. H, I, K, L, dxl. Okay, the first and the third. And the second one is, this is the other direction, right? This is now I have a one form and a vector field. So alpha and y. So I need to write this guy. So there's a minus, minus, so it's plus. And I get contraction with partial k of d of parenthesis missing, of d of this guy. Okay, so now what is this? So partial, so lead derivative can either attack these functions or it can attack this one form. But what is the lead derivative of this? Sorry, what is this guy? What is the lead derivative of this coordinate frame with respect to the coordinate frame with respect to the coordinate vector fields? You can say it.
0.
It's 0. Right? The lead derivative commutes with d, right? I can swap them. Lead derivative, and then the lead derivative attacks this function, but that creates the Kronecker delta ij, which is a constant. So if I hit it with a d, then it's 0. Okay, so this thing is 0. So it means that this thing only hits the first value. Okay, so this really just dxl. Same here. So minus partial j hkl dxl. And here, unfortunately, okay, here I get two terms. So let me how to do it efficiently. Just color. This guy here, calculate it. D is 0, so D only hits this guy. So this is h I j l. Sorry, this is partial derivative with respect to m of h I j l dxm wedge dxl. New index. And now if I contract this, so now I'm hitting all of this with a contraction, and I can contract either, I mean this is a function, so skip that. I can either contract with this or with this. If I contract this with this first thing, then k and m are paired, and I get partial k h I j l dxl. And if it hits if the contraction hits the second term, then I get the minus because I skipped over this guy. And now I contracted k with L. So the result that I get is minus this guy and contracted k and L. So this thing is ijk dxn. Okay, so this is just some not terribly exciting calculation. Maybe it's a little bit cleaner with the Cartan magic formulas, but you know, because if you take general vectors, then you will get some commutators of them, and I didn't want to bother writing them. So. Okay, so now we can call it into Quitterax, and we need to rename this to L. Let's relabel this dummy index L. Okay, L. And then we can collect them, and we get that this is partial I H J K L minus partial J H I K L plus partial K H I J L minus partial L I J K dxL. And it probably won't take much persuading that this thing that you see here is the antisymmetrization. So this thing is, there is some numerical factor which I don't bother calculating, times the antisymmetrization of okay, so if you antisymmetrize things, then you will get 24 bits, but it's antisymmetric in the last three indices, so that kind of cuts it down to just 4 types of terms, and those are the terms. Ones where you take derivative with I, J, with K, and with L, and you can see that the signs work in a way that this actually is the antisymmetrization. So, and since this whole thing is 0, it means that the H is 0. The antisymmetrized stuff, right there. And then, okay, then this was one implication one way, and the other one I don't. Okay, it's actually not much work if I remember correctly. You just have to, essentially the same thing that we did when we checked the Jacobi and everything holds for that case. It's just slightly more, but I think it's very short. But the important thing is that this is to be closed. That's the upshot.
So if you didn't assume that H is antisymmetric and wrote the same equation for this one bracket, would the requirement that is Courant algebroid imply that it's
Yes,
antisymmetric?
we will do that in a second.
Okay.
That's actually like literally 2 propositions away. And one definition. Good. Thank you. Swap them. Any questions for this? Note, by the way, that this is not just any old algebroid. It's actually exact. It is exact. Let me include that as a proof. I mean, if it's a Courant algebroid, then it's exact. And okay. So why is it exact? So exactness means 2 things. The anchor map is surjective. So if the anchor map is surjective, it takes a vector in one form and produces a vector. Is this surjective on vectors? Yes. So that works. And is the rank of that bundle twice the dimension of M? Well, yes, right? Because E is tangent and cotangent, which is twice. So it is exact. So, yes. Good. Okay. Now, in order to be a little bit more formal and maybe satisfy people who like morphisms, so let's say an isomorphism of Courant algebroids. Let's say we'll use call second order primes. So this is simply a vector bundle automorphism. Okay, preserving. It's not a very surprising definition. Preserving the Courant algebroid structure, i.e., bracket pairing in the elixir. Now, okay, a little bit maybe more explanatory. So, vector bundle. What does being a vector bundle isomorphism mean? So, vector bundle isomorphism means that there is a map like this. You have these two vector bundles, but there's also a map on the basis, right? So you have like, you can imprint, this doesn't have to be, well, I mean, okay, so this thing is a diffeomorphism. Okay, so this is M, and this is the bundle over it. This is E. There's a similar thing here, prime and M prime. And I'm saying that there is like these two maps. Let's call this phi, and this one I will call phi bar. And phi bar is an isomorphism here, a diffeomorphism. So we take a point and it gets mapped to some point here, etc. And vector bundle isomorphism means that the fiber above is mapped isomorphically in terms of isomorphic vector spaces into the fiber above that point. So this map here is phi, and this is commutative, so it's commuting diagram. So this is no. So the fibers are preserved. And so when I say preserving a Courant algebroid structure, and what I mean is that if you use these two maps to actually identify one with the other, then the corresponding object will coincide. That's what it means. Nothing too surprising.
Can I ask you a thing?
Yeah.
So if you wanted to write equation manifolds admit structure of exact Courant algebra, then the dimension has to be divisible by 3, which is from what you showed. No?
No. I mean, you see, this example, it worked. No. Sorry, this can be 0.
No, I mean, you showed that the dimension of the fiber in the exact case is twice the dimension of the base manifold. So as the whole thing, it has dimension divisible by 3.
Oh, the total space, you mean?
The total space,
yes. Yeah. That's
which is kind of like strange now, because you have like complex manifolds which have, or symplectic which have division like even dimension,
okay.
or like this quaternionic which have divisible by 4.
But you see, like you should regard this kind of the idea behind sort of is that you should regard the whole thing as being like a new tangent bundle over the.
But then the base is missing half of some of the directions.
Yes, yeah. So that's why it's not really that, but like morally, so you should. So the total space is not the. I mean.
So is there some structure which is kind of more symmetric that like?
I'm not sure, but I mean, where I was going with the remark before was that I won't say that I don't want to regard total space as like your space. It's really, I don't know. It's the whole thing. Okay, now I don't have anything intelligent to say about that. Yeah, it's true. This rank, sorry, the dimension of this as a manifold is 3 times the dimension of M. But that's an interesting observation, but I do not know to make out of it.
No, I was wondering, just if you can make it kind of more symmetric, because now fibers are twice as big.
Oh yeah.
The
No.
base, which is.
Yeah, but I kind of am not concerned about that. And yeah, that's kind of part of the power of this, that you can go away from this. Maybe. But
Why do you care only about isomorphisms?
Because well, there's various answers. One answer is that it is a bit clumsy to define even for Lie algebra, which is kind of like a simpler cousin, to which we'll get next time. The definition of non-isomorphisms is kind of tricky, a little bit. I mean, it's kind of like you can write it. It's not very. It's kind of long and complicated, and kind of the real Okay, let me say it like this: we will get sooner or later to an alternative description of this, which is much simpler, and then you will see that these things are sort of symplectic in some sense. And symplectic manifolds are famously, I mean, it's kind of as a category. It's easy to define isomorphism between them. You can define some sort of morphisms, but they are not like super satisfactory. And indeed, there is like various suggestions about how to define morphisms in that category. So it's a whole interesting business. People use Lagrangian relations and their composition and that kind of stuff. So okay, but at this stage that I wrote it down, it's probably not very clear why I'm saying that. Why I'm only defining isomorphisms.
So if we just erase iso in that definition, that doesn't even make sense, right?
No, it wouldn't make sense. No, because so the problem is that if you for instance, what is the issue there? Like, let's say like if this map, if M goes to M prime, would be something like a curve goes into some two-dimensional object. Then if you have a section of this, it doesn't produce a section of this thing, because for section of this thing you will need to know this in like everywhere.
Yeah.
So okay. So one problem is that although row maps one bundle to the other, it doesn't map sections to sections. Yeah, that's maybe one way to say what the problem is.
Yeah, I don't see it. Can you...
Yeah. So if this would be, let's say you have like, this is R, this is R2, and the map would be that you take this and you map it as some sort of curve, and then you have Courant algebroids. Imagine that now you have Courant algebroids over both. Actually, it's not just ordinary, just any vector bundle. So you have vector bundle over a line, and you have vector bundle over the whole plane. So imagine some higher-dimensional thing hanging. So
but the sections you will pull them back, no? So somehow.
So you want to pull them back?
No, because that's what I will do with sections. So is there something like restriction of Courant and algebroid to submanifold of the base?
Probably that's because the structure of the brackets involves Lie derivatives. So you don't only need vector like elements at a point, but also like full sections that you need to push forward in a sense.
Right. So
you could have a morphism of vector bundles. That's it.
Yes.
And from anchor and inner product makes sense pointwise, right? But
yes, that's right. Yeah.
The bracket
the problem
does
is
not make sense.
Exactly.
Okay.
Yeah. That's right. So So one way is that if you have a map like this, and for sure sections here doesn't produce a section of the whole thing, but also pulling stuff back. It depends on if you pull back. It depends on how stuff behaves around this point in order because it uses derivatives. So it's like the like to get it here, then if you would have a general section over this guy. If you pull it back, then this thing will only see how the section looks like above this line. But the bracket on this side, to calculate it, you will need to know how it behaves in a neighborhood around it because of the derivatives. Does that make sense?
Yeah, but then is there some kind of generalization of this definition which takes into account, let's say, this first order neighborhood? Some kind of additional.
Maybe I never pursued this. I'm not saying that you cannot define reasonable morphisms. We will see a little bit behind some more general class of reasonable-looking morphisms later on. Okay, let me just say that defining. I wanted to avoid defining general morphisms. Like I'm sure you can, and in some way, but I don't need it here. And I wanted to blame it on the simplicity of this. It's very kind of symplectic in the
It's not only simplex. Yeah.
Sorry?
Yeah, it's complicated already for ordinary.
Yeah.
So, like, you can look it up in Mackenzie
So so
And
this symplectic
and
viewpoint.
pairing makes it even more complicated.
Oh, I see.
But if you have a symplectic manifold, you can have symplectic submanifolds, no?
Yes.
Well, it goes only one way, you know, in symplectic, like from between dimensions.
Right.
If you would like to have pullback, you know, so you can go.
But you can have
Yeah, you can have more. Yeah.
You can have
That's
inclusions kind
true.
of.
That's true. Yeah. Yeah. So okay, maybe I wasn't very precise about what I was saying before, but yeah. So but it's general vague idea that for symplectic it's kind of an involved story already because as Brandon said, you can do it one way but not the other. So that's why people propose to correct ways to look at Lagrangian correspondences. Lagrangian relations. Sorry, Lagrangian relations as morphisms in the category of symplectic manifolds, and that seems to be kind of also a reasonable thing to do in here.
Yes.
And but all of that will kind of become much more clear and transparent once we actually go to the description when you can shrink this to half line, and then you will see that
I
actually.
should advertise it.
No, but he already mentioned that. He also
There
said
is dissociated paper.
Okay. But he also said that this is kind of
Correspondence.
secretly symplectic indeed,
Yes,
right?
yeah.
But then this argument, like Drano says, that in one way you can include symplectic submanifold inside of the bigger one.
Yeah, that works.
That works. So then if you
But
pass
that's
it,
good enough, you know.
yeah, but does it apply here as well or not?
Yeah, well, with
Yeah.
So
So-
the
so-
pairing, but it's not the only problem. Yeah.
So does that exist one direction of
Yeah, it exists.
morphism?
Yeah.
Like
I think so.
kind of inclusion.
I think so. Yeah.
Yeah, if you forget about pairing, then you can have satisfactory notion of a morphism between Lie algebroids. That's like a bit complicated but textbook.
Yeah, but we will also get to that one in the graded geometry, and that one will also look similar. It will be simply a map of two spaces where the vector field maps to the other.
Okay. And when you talk of the algebra, that's a special case of this?
Courant algebra, no, it's not special.
So it's a different thing, right?
Yes, but they're related. I mean, one way. From Courant you can easily. I will get there later. Yeah. Okay. So yeah, probably the most satisfactory thing to say is that I'm not introducing because I don't need it at the moment. So maybe it was wrong for me to say that you shouldn't go beyond, but for what I want to now in classification, I care about isomorphisms. But yeah, those were very points. Okay. Okay, so now let's do. Let's call this algebra somehow. Okay, I decided call it exact Courant algebra over M with H. Okay, so the silliest name ever. And now the proposition says, next proposition, before stating the classification result, this thing says that there exists an isomorphism covering the identity. Identity over M. Okay, so covering, I mean, you take like this thing, you know, in this case you would say that phi is covering phi bar. So the map upstairs is really going above the map downstairs. So there exists an isomorphism covering the identity between ECA and H and ECA and H prime, if and only if H and H prime are homologous. Okay, I'm not terribly satisfied with this, with the form of this sentence. So if anyone has a better shuffling that makes it more, but the statement is clear, right? Like if you have two settings, then they are isomorphic if only this is homologous. But the first part of the sentence is kind of long, so if there is a better I define it where you think that you're from.
Generalised mean
Exactly.
exactly. Ah, so
So this example is called ECA MH.
okay, but then the theorem that any exact will be isomorphic. So that be something like this.
Yeah.
Or it's not this. Yeah.
No, if H is exact, then this is the same as the one where without any H.
Okay.
That what you mean? Or like I mean, we define a class of algebra.
Yes.
So for any manifold and any closed free form,
Yes.
you can define an object like this, and I'm saying that.
Specific model of like.
Yeah, and I'm saying that sometimes it might be that those things are isomorphic to each other. Maybe not all of them are actually different. And I'm saying that happens when there are common numbers.
Okay.
And if only if that.
Okay, so if they represent the same common class, then you say that they are isomorphic.
Yes.
Okay.
Yes.
But you also called them exact here, and you had exact also. In
Oh,
previous
sorry.
definition.
There's two meanings of the word exact.
Exactly.
Sorry. So.
The one was in the definition, not the one you said that it's basically the short exact sequences.
Yes.
Exact.
Oh, I didn't yet define. Okay, so let's say that this E is mysterious for now. We don't know that it's
Okay, so my question was if you are going to prove.
Yeah. I'm going to prove that. Yeah. I realize. Okay. So far, let's say we don't know what this E stands for. Okay, so it's just some strange letter that they wrote in from the Courant algebra. Thank you. That's right.
It's only in the proposition. Like this.
Okay, yeah. We are saying that this is exact. Okay, yeah.
No, but not any exact.
Yeah, we don't know that yet. Okay, so now we know that E stands for exact, but we don't. But so far it's just a name, and the theorem afterwards will say that actually all of them are of this form.
So you said it's spoiled like.
Well, no, I just say that given M and H.
It's spoiled in a movie that now we kind of already know.
Okay, yes, okay. Okay, that's fair. I think we need to break. Okay, so yeah, I'm just saying, for any manifold A3 form, we can create an exact Courant algebra, which we will call exact Courant algebra associated to M and H, and so far we don't know anything whether this exhausts all possibilities or not. We might learn that later after the break. So let's make a break, I think, for 10 minutes. Oh, okay. Okay. Okay, so let's prove this freely hanging proposition. Okay, so the important technical thing in here is this thing that we are understanding this as isomorphism which covers the identity. That's just it's just the way it is. Okay, so wrong shot. No, right shot. Right. Proof. So what does this mean? What do we want? So we have these two algebroids. They both have this form. And they are both algebroids over M. And now the fact that they are covering the identity, sorry, and let's suppose that this one, so each of them has like a pairing, a bracket, and an anchor. Okay, pairing, bracket, and an anchor, except this bracket here uses some H, and this bracket uses some H prime, according they enter in that way that we defined before. So now the fact that it's an isomorphism covering the identity, it means that essentially this map is the commune. So it's really a fiber, at every fiber, at any point on M, I'm looking for a way to translate the corresponding fiber here to the corresponding fiber there. And I want to preserve all the structures. So let's look at them one by one. So for instance, what does it mean that the anchor is preserved? So let me draw the same thing again. And each of these things, well, there is the anchor map, which is simply projection onto the first vector, and here the same. And I want that the anchor is preserved, so I want that this is the same actually. Okay, so now what are the possible maps from this guy to this guy, which commutes with this guy, with this row? So that's the first thing. So let's call it phi. Okay, so after a little bit of thinking, you will see that after I project it, I get the vector field, and I should get the same if I project it here, which means that after I apply this, then the only way is to have a vector, and then potentially something. Potentially there is some. This is some one form. Okay. So if I apply this isomorphism on X, I need to get X, and potentially I can get one form. And if I apply this to a one form, which was mapped to 0, it should still map to 0 here, which means that it should also be mapped to a one form. So let's call this, I don't know, lambda alpha. Okay, this thing is a one form again.
Excuse me, so this is like a new condition you impose on the isomorphism that it also has to preserve the anchor?
Yeah, no, that was part of the definition. It preserves all Courant algebroid condition, meaning
okay.
bracket, anchor, and pairing.
Okay, good.
Yeah, thanks. Okay, so now we know that, well, the only thing that any isomorphism at most is given by these two things. Something that transforms a vector to a one form, and the same, the one form to a one form, and they need to be pointwise. So that's good. So that's the anchor. Now, what about the pairing? So, this is kind of the first. So what about the pairing? So we know that, for instance, we want to preserve the pairing, so we want to have something. Step 1, the anchor. And this is step 2, pairing. So if I preserving this means that I want this thing to be the same. Okay, let's substitute this. So we know that this thing, left hand side here. Right hand side is for simply contraction of one form with a vector field, with a vector. Here I apply this map, so on the left I would get a vector plus some one form, and on here I would get a one form. Okay, but how does the pairing works? It works in a way that it's, if you pair a covector and a covector, one form is 0, so this thing actually doesn't contribute. So you only get this paired with this one, which is simply the same as L alpha, lambda alpha, acting on X. And you see that the fact that these things have to be equal for any alpha, any X, means that alpha actually has to be, lambda is the identity map. So it should not change. So actually so compatibility with the pairing and with the anchor tell you that the only freedom in choosing this map is that you need to specify this omega. But moreover, this omega cannot be anything, because if, for instance, if you do phi x, phi y, this thing should be the same as x and y, which is 0, because pairing of two vectors is 0. So this thing tells you that, what is this? Is x plus omega x and y plus omega y. So pairing works in a way that pair vectors with covectors, so this is omega y on x plus omega x on y. And you see that the fact that this has to be 0 means that this omega, which in principle here in this picture, omega was a map that, how did we call it? Took a vector and it produced a one form. So, which is the same as to say that it was a section of T star tensor T star. Okay, so it's a covariant 2 tensor. So here you see that that 2 tensor has to be antisymmetric. Okay, so the conclusion from this one is that omega acting on X is in fact contraction with some B, where B is a 2 form on the manifold. Okay, so that's what pairing and anchor give you together. They tell you that the only possible isomorphisms are of this thing which preserve. The only possible vector bundle maps which vector bundle isomorphisms which preserve this one and this, the row and the pairing can be parameterized by the B form. And you can check that looking at alpha and looking at the last remaining thing actually doesn't change anything, because this thing that if you have two one forms, And one form gets mapped to itself, and so this thing is 0, just as alpha beta should be. Okay, so this thing doesn't do anything new. So the conclusion is that vector bundle isomorphisms covering the identity map and preserving pairing and the anchor, they are precisely given by two forms. Okay, so far this is just to say, okay, so we know, sorry, between vector isomorphism of T plus T star, T m plus T star m, which cover the identity of those things. So now there is the last remaining thing, and then we need to check what happens with the brackets. Like, what is the possible, when can we actually have such a thing, that the bracket will be preserved. The last thing is to check this condition. Okay, and recall that we now have two algebroids, like one of them has h and the other one uses h prime. Okay, so let's write this thing and calculate. So, well, let me just say x plus alpha, y plus beta, and this thing should be equal to y x plus alpha, phi, and y plus beta. Okay, and again, this is the bracket that uses h, and this new one after we use phi, this thing is the bracket that uses h prime. Okay, so let's just calculate. So I remember phi. The only thing that phi does is that if you take this guy, it creates this plus this, and then plus this contraction with b. That's the only thing that happens. Okay, so let's just calculate. So if I wouldn't have phi here, let me calculate the inner stuff first. So this is least derivative x y plus least derivative x of beta minus I y d alpha. That's what would happen if I had no phi. Now what does the phi do? It takes whatever we had and it just adds contraction of beta with your vector. And the vector here was this guy. So I only need to add one thing, and that's sorry. This bracket had h in it, so the full bracket was actually looking like this. And now if I apply phi, I need to add in that extra. So that's the left hand side. Now what is the right hand side? The right hand side is really x plus alpha plus I x beta and y plus beta plus y I y b of x alpha y beta. Yeah. And the bracket of that is parenthesis lxy plus the derivative of the one form, so lx on beta plus iyb minus contraction vector d of the one form here, alpha plus ixb, and then because this bracket was twisted by h prime, doesn't h prime present in it, we need to add this thing and use this is the only vector. There's x and very one x. Okay, so if there is an automorphism between these two structures, then it needs to do precisely this. Now let's check when can this be satisfied? I'm looking at the beginning and the end. And what does it give me? Okay, so this thing is on both sides. This thing and this thing is also on both sides. So when I get this x, y dot plus I L x y b has to be equal to whatever is L x y L y b minus I y plus u I x b plus h prime x y dot. And this needs to hold for all x and y. Okay, so now how do we do this? Let's put the ages on one side. And what do we have on the right? This one, okay. Yeah. Okay.
Piotr, ten první naprav, teďka ten zlej naprav,
Ještě no?
No, teraz si napísal ten první napravo, teraz ještě ten napravo.
Jo. Yes, thank you. Okay, so I can take b out, and or even better, I can just say, look, this is the commutator of lead derivative and contraction. So it's this one minus the other way. This cancels this. And if I write the lead derivative in Cartan magics using Cartan magics formula, then this one cancels this one. And the thing that I get at the end is just this one term minus with an extra minus, so that's I y I x db. Okay, and which is the same as db with x, y inserted. Okay, so we see that well, this is the condition. So if you have an isomorphism between Courant algebroids of this type with H and the one with H prime, then well, you can only have that if there is a two form that relates them, and it needs to relate them by this formula. So that should be it. And conversely, any two form that's any two one. Okay, does this work? Okay, and now we can write down the maybe one more definition.
So if someone gives you this exact Courant algebroid, but not the specific one, but the other one, can you somehow extract the homology class of
Yes.
H?
Yes.
Like directly from...
Yes, and we will see how in the next proof. Yeah, you need to choose an isotropic splitting of the exact sequence, and then the image of that will give you the three form in a concrete way. And you then take the homology class of that. Yes, and then that's actually, even though it sounds a bit abstractly, there is a way to construct Courant algebroids, which are kind relevant for physics, like for dualities and things. And if we construct them in a way that it's not clear from the way they look like that they are actually exact, what they actually are, and then you can determine their cohomology class if you wish, using this maybe this thing that you asked. And we will get there later on.
And if they are not exact, can you still extract some cohomology class, or that not determine them, but maybe as part of data, or it's not even?
Well, in the transitive case, you can do something similar in some way, but this one is a bit more messy. First of all, you don't have a global classification. I mean, you do it in some unuseful way, but like not as nicely as the one I'm going to write. And but you can create a lot of them if you play with some principal bundles with vanishing corresponding class, and then there is some analogous story there, but it's not as easy as this one. Okay, good. So now we are ready to state the theorem. No, the definition. Okay, to state it, so definition. Okay. So for a Courant algebroid, sometimes I would just say, I mean, Courant algebroid really has a bracket pairing and an anchor, but I will just, in short, write either just E over E to M, but I really mean the whole structure. So for Courant algebroid, we define the group of automorphisms maybe covering the identity S, and now I will write out identity E, and I take this to be simply isomorphisms of E to itself, covering identity. Okay, so we all put the only thing we can. But okay, I just want to say that it follows from this preceding thing that if you look at automorphisms of your given Courant of this one that we studied, of this ECA MH, and you look at what is its group of automorphisms. So first of all, you know that any automorphism that preserves only the pairing and the anchor, it has to be given by a 2 form. And the only way that it preserves also the bracket is that it doesn't change, is that this thing has to be closed, so that it doesn't actually move you from one H to another. So this thing is simply closed 2 forms. This is CL. So closed 2 forms of M. Okay, and now let's do the theorem. Okay, theorem. And so this is due to Paul. I mean, actually, okay, Paul Schemera is an important figure that I should have maybe mentioned already before. So, like, lots of the stuff that you see is, and that especially the stuff that you will see from now on is actually his doing. So he was the creator of that. So classification. I kind of split it into this chain of propositions. So already the statement that we've seen so far was part of the classification. But let me state the theorem here. Classification of exact Courant algebroids. And this thing says, first of all, every exact Courant algebroid over M is isomorphic to ECA-MH for some H closed free form. And hence, together with the proposition that we just shown, so thus exact Courant algebroids over M are classified by the third theorem called classified, if you wish, in a sense that this is the end. Classified in the sense that I take Courant algebroids up to identification, up to isomorphism preserving the identity, covering the identity. So this is up to isos covering identity, to be completely precise. Okay, so the only thing proof for us is to show the first part. The second one just follows from this automorphism, from this proposition that we have. So the only thing we meant to show is to show that actually every exact Courant algebra has to be of that type. So let's prove that. A little bit maybe longer than the previous proof, but also quite nice. So, okay, is the statement clear? Good. Okay, so let's say we start with a given abstract exact Courant algebroid, E over M. So there is several parts to the proof. So the first one, I decided to split it in several parts. So first claim is that there, remember, exactness meant that there was this sequence. Star, row, and this was exact. Okay? Starting with exact Courant algebroid, okay, so we have that this sequence is exact. This first claim, there exists an isotropic splitting, or in fact Lagrangian splitting tau of this sequence, which is the same thing as to say there is a map tau that goes from Tm to E, such that it goes like this. Tau, such that it's a splitting, which means that if I apply that and then I go back using the anchor map, then I get the identity. And Lagrangian means that image of tau inside E is Lagrangian. Okay, this thing has a pairing. So now how do we show this? So, well, there is proof. I mean, it's a sub-proof, really. I don't know how to note that. Proof of the first part of the proof. Well, one way is to use partitions of unity to kind of glue things together. So you can use partitions of unity to show that you always, any sequence of vector bundles is split. So if you just have vector bundles in a smooth category, as we are working with, then every vector bundle, every exact sequence of vector bundles is split. So you can always find a map satisfying this. But the trouble is that you want it to be Lagrangian, and that's kind of, you have to be a little bit careful there. But you can do that, but I will instead use a trick that I got. So I'll use this a trick from the book from Garcia Fernandez in the Streets. One of those that I think I mentioned at the beginning. And the trick goes as follows. So choose any splitting, not Lagrangian, just any n is splitting tau 0. Okay, so I want that row follow tau 0 is algebroid. And now I will modify and claim that there is like a canonical, there is like an explicit formula. And then define a new one, new map, tau, which I will define to be this minus 1/2 rho star tau 0 star tau 0. And what I want to claim now is that this thing is a Lagrangian splitting. Okay, but let's first check if this is actually well defined and meaningful. So these guys, they should go from Tm to E. So tau 0 does go from Tm to E. Now what about the second term? So how does one write that? So here in the second term, I start with tau 0. So tau 0 sends me from this guy to E. Then I apply tau 0 star. So tau 0 star is a match that goes from the dual of this one, which we know is the same by declaring. It goes to the dual T star M. So far we are here. And then we apply rho star. And rho star again goes from the T star M to E. Okay, so we have a map that goes from T to M to E. So it seems to be well defined. It is linear, because, I mean, well, this is just composition of linear maps. So the things to check is, okay, first thing, whether is this thing actually a splitting. So we know that this goes from T and to E. And what happens if I apply anchor after I apply tau? Well, right. So the thing to remember is that if I apply rho to this guy, I get 0 because rho follows rho star is 0. Okay. So here, using rho star 0, I get that this is the same as it's just composition with tau 0, which is the so this works. Note also that this thing tells us that, well, in particular, this implies that tau is injective. I mean, because after you post-compose it, you get identity. Yeah. Okay, now the other claim. So let's say that I take. So let's try to check Lagrangianity. So how do we do that? So let's pick any vector. And now let's calculate what is tau x, tau x. I could have chosen, I could have chosen tau x, tau y, but I don't know, it would be twice as long. So let's just do this. So what is this thing? Substitute, it's tau 0 on x, minus 1/2, rho star, tau 0 star, tau 0, x, and the same, tau 0 x, minus 1/2 rho star, tau 0 star, tau 0 x. Okay, now, right, so the easiest part is to remember that exactness tells us, exactness implies that the kernel of the anchor map is coisotropic. Exactness tells us that kernel of rho, if you take the complement of that, by our lemma from the beginning, this is the same as annihilator of kernel, so this is image of rho star. And by exactness, okay, exactness here tells us that this is precisely kernel of rho. So we see that kernel of rho is Lagrangian. Or equivalently, image of rho star is Lagrangian. The same thing. Which means that the pairing of this guy with itself is 0. Okay? Lagrangianity means that it's isotropic and half-dimensional. So isotropicity means that if I take any two elements in there and I make a inner product, then I get 0. So pairing this one with this one is 0. So I only get the only non-zero stuff is if I pair the first guy with itself, and if I pair the first guy with the last guy, and I get it twice, so I get minus tau 0x, and then rho star, tau 0 star, tau 0x plus 2. So because I put xx, then I only get, this thing would in general have 3 terms, but I'm saying that the last one of them vanishes because of Lagrangianity. So here is the fact that image of rho star is Lagrangian and principal in particular isotropic. Okay, and now the only thing that I'm not going to do now, and that's not to be an abuse of notation, but it's true if you check the details, is that I'm just going to move this row. This is really this is the dual or adjoint or transpose map, so I can just move stuff here and I would remove the star. Okay, so this is the same as rho on tau 0x, tau 0 star, tau 0x. But this is identity, right? I can kill it, and then I can move the tau here. And I get precisely tau 0x, tau 0x, and something cancel. Okay, so a little bit of a cheap trick. Oh, okay, we haven't finished yet. So we know that this is 0 for all x. So by polarization identity, we know that it's actually true for any x and y. And hence, image of tau is isotropic. But it's not just isotropic, it's also the dimensions were corrected so that it's actually Lagrangian because tau was injective, so the rank of image of tau is the same as rank T, it's the injectivity. Okay, sorry. Which is the dimension of n, which is precisely half of the rank of the whole guy. Okay, so these two things tell me together that it's actually Lagrangian. Because Lagrangian is isotropic and half-dimensional. Okay, so that's a small square at the end of this part of the proof. There's always stuff written on this board. Very inconvenient. Maybe I should mention again that because if there is people who are actually going to take an exam from this, then don't bother about remembering these kind of random formulas. It's just, this is kind of an important theorem, but just a brief outline of the proof is all that one needs. There is a way to, you can just say that, yeah, there exists a way to have a global Lagrangian splitting, and details are left to whoever.
So this correction term, can we understand it as like a B transform, as a shift by a two form?
Well, it's not a shift because it's a map from tangent bundle to. Oh, the correction term, sorry.
Is it the space of?
No, because and we will get there, but the reform shift transforms you between isotropic and other isotropic, and this one is not isotropic.
Yeah.
You want to have non-isotropic. This thing is following me. Yeah. Tell me when I'm waving because I'm not aware of that.
So when he does this, the other starts following you, but
I
he
think
does it very secretly.
Yeah. Okay. Okay, so now, okay, this is kind of the technical part, now comes the fun part, in relatively speaking. Right, so the second claim is that now we suppose that we have the tau thing. Okay, so we start with our Lagrangian splitting, and we define a map to E. And the map goes as follows. So you give me a vector and a covector, and I map this into, and now well, there is only one thing I can do with the chosen tau. I use tau to map x, and I use rho star to map alpha. Okay, because remember again, rho star was going from covectors to E. So, okay, so take tau Lagrangian splitting as above, and then we can define a map like this. And now the claim is this is an isomorphism, and not just that. This thing is a vector bundle isomorphism. Well, covering the identity, but that's kind of, this is point-wise, so covering the identity. And it also preserving this thing. So this was E was a Courant algebroid, so we had a pairing, and here we have that pairing that we seen before. The standard one. Is an isomorphism preserving a pairing and also preserving and satisfying that if I let's call it capital Phi. If I do capital Phi and then I apply rho, so it kind of preserves the increment, if you wish. So the natural map to Tm on the left is, and the map to Tm from here, they coincide by this. Okay, so proof. Okay, so we have a concrete map. It's a statement here. So we have like Lagrangian splitting. We have the data. We can construct this map, and now I want to check that. First of all, it's an isomorphism, and it preserves the pairing and that. No, actually, okay. So, okay. So the proof is very simple. We just recall what we know. We know that the image of tau and image. Okay, so let me say that. Tau, both tau and rho star, so both the ingredients that we have here, are injective. And their images are Lagrangian. Okay, so for tau it follows by construction. We need to take it to be Lagrangian splitting. For rho star it follows from this one. And the injectivity follows from, well, here because it was a splitting, and here because it was an exact sequence. Okay, so the
And rho star being image of rho star being Lagrangian, that's the other rho star being 0 at the beginning.
yes, I mean that's also this claim. Yeah, that's image of rho star is Lagrangian. It's the same as kernel, and it's coisotropic, and if the dimensions group, it's Lagrangian. Okay, so I'm trying to recall how this goes. So what do we need to show? So, oh yeah, so they are Lagrangian and images of the image is Lagrangian and also image of tau intersection image of rho star should be 0. Is that true? So let's check. Let's check this last statement. So image of tau. Yeah, that should be. Oh yeah, because the splitting. It's a splitting of a sequence of. So by kind of because tau is splitting. So is the exponent? No, maybe I should say so. Okay, so suppose that we have if x, if let's say u was in the image of tau, then and also in, let's say something is in the intersection. So it's both here and in the image of rho star, but image of rho star is the same as kernel of rho. And we know that if you apply rho to u, then you should get rho of u is the identity on u, so it's u. Sorry, rho of okay, this thing should be easier than I'm making it. So if okay, so rho of u is 0 if and only if u is 0 because tau was injected, right? No, wait, what am I saying? Okay. Sorry. We should not be getting lost in such simple things. Okay, so if it's both in the image of tau and in the kernel of rho, then if I apply a rho onto it, then I should get 0 because it was in the kernel, right? Because it's in the kernel. But because it was image of a tau, then it means that u is tau of some x. And well, and the above thing then tells us that rho on tau of x should be 0, but rho of tau is the identity, so x is 0. Okay. So yeah. So there I have the intersection.
Sorry, just to be clear, so you are looking for now at the Whitney sum of the tangent and cotangent now just as a vector bundle?
Yes, just as vector bundle. This is just vector bundles.
So this is just a morphism of like
Yes.
a Riemannian vector bundle?
Yes, that's right. Yeah. Yeah, I apologize for this. But okay, so you see that this gets mapped into tau, by tau, this gets mapped by rho star, and both of these maps are injective, and their images are have 0 intersection, and they span the whole space. So this is in fact an isomorphism. Okay, does that make sense? Okay, so these two things should imply that yeah, it's an isomorphism. Phi, an isomorphism, and the fact that it preserves. Let's see. What about the other two statements? The first statement says that it preserves the pairing. So if I do capital phi on x plus alpha, capital phi on y plus beta, and this thing should be the same as x plus alpha, y plus beta, which we know is just alpha y plus beta x. And what does it do here? Or is this actually clear? Should I wait? Sorry, let's it simpler. So this thing is Lagrangian, this thing is Lagrangian. The image of this is Lagrangian, the image of this is like it's in something Lagrangian. So if I take inner product of x with some y, then it was Lagrangian here, it will be Lagrangian here, so the inner product is 0. So the only thing to check is actually what happens if I pair some x with an alpha, phi of x, phi of alpha. That's the only thing to check. Whether this thing is the same as pairing of x and alpha, which is alpha of x. But now looking here, so what is this? This is tau of x paired with rho star alpha. And if I again throw this rho to the left, then I get rho tau x alpha, and rho tau is identity. So this is just x alpha of x. Sorry for the downward tendencies of it all. And the last thing here. Last thing is to check this condition, which says that, that if I define kind of like I mean, this thing on the left, so far I'm not working with brackets, so I'm not claiming any Courant algebroids. I'm just seeing both sides as like vector bundles with pairing and some anchor map, and I'm saying that this map preserves the anchor map. Okay, that's what this statement is. And that should somehow be easy to check. So if I take this one, and I apply it to x plus alpha, then this thing is rho of tau x plus rho star alpha. Well, rho followed rho star is 0, and rho follows tau is the identity. This is x. Okay, so that was a bit painful, but okay, so yeah. Okay, so what is the axiom of this thing? So we now know that if we forget about the bracket, then any exact Courant algebroid has to be of, I mean, we essentially prove the theorem. If we don't care about the bracket, then we know that every exact Courant algebroid has to be of that form t plus t star with the anchor and pairing given by these standard formulas. Or more precisely, we know that for any exact Courant algebroid, there exists an isomorphism covering the identity, which identifies it with one of our model cases. Now, what about the bracket? Conclusion so far was that our exact Courant algebroid E is isomorphic this is one way to say it. So this is isomorphic to Tm plus T star m with the anchor given this, the pairing given this, and with this will be sort of tautological maybe, but okay, whatever. And with the brackets u of v given by phi inverse phi u phi v. Okay, so what happened here? I'm saying that now we build an isomorphism between our Courant algebroids seen as a vector bundle with that vector bundle. And if I do that, then using that isomorphism, both the anchor map and the pairing they match. So now this is kind of a trivial statement. I'm saying that if I now use the isomorphism to bring the brackets on E to the brackets on T plus T star, then that will give me a Courant algebroid. That's a sort of like not really tautological, but like I'm just saying that because those two things are identified, I just induce a bracket by pulling it back. there was there was no new content in this statement. I'm just rephrasing what we said above. But now I want to use it in a way. Now essentially the only thing that for us to remains to do is to consider all possible Courant algebra structures here, 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 and check what is the most possible bracket that you can get there. Okay, is the philosophy clear? So again, if I wouldn't care about the bracket, then I'm done. I know that every Courant algebra is isomorphic using isomorphism covering identity to this guy with this anchor and this pairing. And so there is a vector bounded map that does this. So I just use the vector bounded map to kind of bring the bracket to that guy, and by construction this thing will be isomorphic. This thing with this bracket is isomorphic to the original E. That's okay. So
can you repeat the statement? So this is like a definition of a new bracket?
yes. So yeah. So yeah. So yeah. It's kind of okay. I said it in a messy way.
Yeah, but I think it's mostly okay.
Okay. So I'm saying that if you forget about the brackets, then you have these two things, and there's an isomorphism between them. Now I'm saying that you can, because it's an isomorphism, it really maps every point in the fiber in the vector bound to some point there. You can identify the two things, and you can essentially look at what the bracket looks like in terms of the structure on the left. And that's what I meant by here. And this thing is just saying, yeah, this thing is just said that this is just the concrete way of saying that I identify the two things and I look at the bracket. So this just means that I take the pairing of E, but on T plus T star. So I identify them and I just look at what the bracket looks like. Yeah, I'm sorry. There's a little like nothing deep in here. I'm just making confusing statements about. Okay, but does it make more sense?
Yes.
Okay, good.
So now we have like two pairings and two same anchor maps, like identical ones, but you are asking what is the kind of freedom in brackets? That's what you.
Yes. So now I want to kind of turn the problem. So we now know that every exact Courant algebroid has to look like this. It has to look like this with this anchor, with this pairing, and I will just kind of take that, and now I will just check what is the only way the bracket can look like once I fix every other structure. So to conclude, what is the most general bracket that makes let me encircle it in color. That makes this into a Courant algebroid.
So now that bracket there is like the most general bracket by how it was constructed.
So the way we constructed is that we have no idea what this is. I mean, it was some abstract given stuff, and because this is all just abstract, I just know there is a map and it looks somehow, and I have no idea what it will look like. So instead of looking at what it looks, so instead I'm just trying to see what could this, forgetting this formula, I'm just like checking like what is the most possible way to actually build a bracket in there that it will work. And it will turn out that the only thing you can do is to have that bracket with the H.
Yes, exactly.
Is it okay?
Yes.
Okay, thanks. Yeah, I spent some time on making this as little confusing as possible, and and yeah, you see that it didn't work very well. Okay, but at least the second. This is now a very concrete statement, which is very easy to check. So, okay, so what is the statement? We fix now we identify everything, so we now have this bundle, this anchor, this pairing, and we just have some bracket. And let's see what the bracket could look like based on the fact that we know that it needs to satisfy the axioms. So for instance, we know that there is this axiom. Sorry, no, this one. Yeah, that. This is first one. So this is, we know that this is true for any Courant algebra. If we do this one, this needs to hold. But now we know what the right hand side is, right? Because we already know what our anchor is. The only thing that's unknown is this bracket here. So this thing is just the x and y, because the anchor just keeps the vector part. Okay. While here on the right hand side, sorry, and this maybe I should not, it is probably the right time to distinguish things. So let me put in the subscript. So this is the bracket on E. Okay, this is the one that we are looking for, bracket on E. While the bracket on the right hand side, this is the bracket of commutator vector field. Okay, so this is the commutator vector field, or otherwise this is the linear vector. Okay, so what does this thing tell us? So I use this only this axiom and nothing else, and the form of the anchor. So this thing tells us that if I take our bracket, then I know that its vector part has to be this and only this. And then there is like some one form stuff. But what this thing tells us is that if I apply anchor, which means that I look at the vector part, I know that the vector part is this. The vector part is fixed, it's just the linear derivative. The only thing to remain is to check what the one form part can be.
So, so that the bracket on E should eat elements of E, so x and alpha are.
Yes, this is a vector field, and this is a one form.
So like technically it's not the bracket only, but the one on Tn plus T star.
Oh yeah, sorry. Now I only have this guy. Sorry. Yeah. So Tn plus T star.
Right.
Well, okay, but I mean, I'm just.
You're identifying those by phi.
Yeah. Right. Yeah, that's right.
I was confused by identity.
Yeah. Sorry. Yeah. I mean that. Yeah. And just saying that this axiom tells us what the vector part of that bracket is. Whatever the bracket actually is, we know that the vector part has to be just this thing. Because we know that such an axiom holds in general for Courant algebras. Does that make sense?
Yeah.
Okay, thanks. Okay, so now we fixed that bit. So let's look at the other ones. So there is the other axiom that tells us that, maybe I'll write it in general. So this thing was, so we know that bracket preserves the pairing. And so let's see what that is. So what is, so we know all the ingredients except for the bracket. Put E there. Okay. So what does this give us? So if I substitute, let's say I take U to be a vector field, V to be a vector field, these two guys are vector fields, and I take the third guy to be a one form. Okay, so what happens here? So U was a vector field, so if U was a vector field, rho of a vector field is just a vector field itself. V and W are vector field in one form, so the pairing is a pairing of vector field in one form. Okay, so this is the left hand side. And the right hand side is that we have this unknown bracket of U and V, X and Y, E, paired with alpha. And here the same, Y, X, alpha, and E. Yeah, okay. Okay, so I just substituted. Now, can we get some information about this? So first of all, we know that this thing looks like, that we determine, this is the lead derivative, and it has some one-form stuff. But one-form stuff paired with one-form stuff is 0. This thing we don't care about. So we can extract what this guy is. So we know that, we also know that whatever this thing is, it is purely one form. So this is a omega 1. And we know that if you pair it with y, so we know that if you take this x and y, x and alpha, and you pair it with y, then it has to be this minus this. So it's x on alpha y minus contraction of LXY into alpha. Okay. So I'm kind of using the axioms always in a way that I get only one unknown stuff and I kind of determine its form from there. Here I use this thing to determine that the vector part, what the vector part was, and now I use that in one step to kind of determine what this thing is. So what is this thing? This thing here, again, this is just commutator of link derivative to contraction with respect to y. And what is this thing? This thing is secretly, you contract alpha with y, and then you apply the derivative of x. So that cancels the first term. And we are end up with contraction on Lx alpha. And remember, this was a one form. And what kind of one form is it? We see, if you look here and there, that the one form, the result of this bracket on E, or E, is that thing. So it's lead derivative alpha with respect to x.
How did you know that it was a one form?
Because I know that the only way to get a vector here is from vector to vector. Right, that was the first bullet was that determine actually all the vector part of all possible combinations. Thank you. So yes, this is first observation. This is the second observation. Oh yeah, okay, maybe I should have said this other one as well. So, right. So now let's take the same thing, but now let's take all of them to be vectors. Okay, all of these guys are vectors, vector fields. And let's look at this axiom. So if all of them are vector fields, it means that vector field with vector field is paired to 0. So left hand side is 0. And what is the right hand side? It's this one. So it's x, y, e pairing z plus y, x, z here. And well, and we know that this thing is the lead derivative, right? That's what we determine, plus some one form stuff. So one form stuff. And here the one form stuff is actually relevant because this thing now doesn't pair with the vector. Right. Okay. So now how does the one form stuff look like? So let me write here. So in generally, this thing we know that it has to look like this, and let's parameterize this one form part by some thing. So let's say this is some map xy, and this map xy. Sorry, the map theta is something that goes from E tensor E. No, it's something that. It's something that eats two vector fields and produces a third vector field. no, sorry, form, sorry. Right. Okay, so I substitute it here, and what do I get? I get that this is theta of x, y paired with z. And here I have E missing. And this is xz, and then paired with y. Okay, there you go. There is one more step I forgot to put in the notes. Okay. Oh, yeah, okay. Okay, okay, so given that, okay, I would probably need like 10 minutes to finish this, and I since I don't want to go over time, and let me maybe wrap it up here, and let's say, okay, and next time I will maybe briefly try to recap what was happening in this proof, because I feel like my way through. No?
Yeah, no, maybe comments also, but no, if it's
Okay, well, okay, then I can do it in 5 minutes. Well, okay, there is the, okay, so what I'm now trying to understand what exactly is the one form part if I take commutator of two, if I take a bracket of two vector fields. And I just parameterized it by some abstract thing. One thing I forgot to think is that need to check now that this thing is actually tensorable. So if I put this thing, it is this guy, and if I put it yeah, so and that follows from, okay, need to check this, okay, this is one thing, and the fact that it's antisymmetric. And okay, so let me leave this part as an exercise. So to check this, you need to use axioms. Let's not include the label them. I think it's axioms 2 and 4. So on this bracket on the left hand side. So if you use those axioms, then it should come out. Then you should see that this thing holds. And the implication of that is that the bracket, no, okay, sorry. The implication is that the theta is secretly a tensor that eats two vectors, wedge to t star, tensor t star, tensor, yeah. So it should be something that it's antisymmetric. It eats two things. It's antisymmetric in them, and it's a tensor. And it produces a one form in the end. Okay, so it's a tensor of this type. This is what comes out from here. Follows. And now if I come back to this point, then you see that this statement here, which let me call it heart. But now by heart, we know that it's actually antisymmetric also in the last two slots here. See? So theta is actually a section of wedge 3 t star. So it's a 3. And hence, actually, is that the bracket of x and y, the full one, is given as lxy, and then some 3 form xy dot. Okay, where for h some 3 form. So now I rename theta to h to match with what we had before. Does it work? So okay, so now we know many things. we know that if whatever this abstract bracket was, in order for it to satisfy the Courant order axioms, we know that on vector fields it needs to look like this. We know that on vector field in one form it needs to look like this. And the only remaining thing is to check what it does if I do the other two things. Like what is alpha x for one form in a vector field, and what is alpha and beta if both of them are one forms. And this is much easier. Well, this is very easy. This is I guess I call it axiom 3. And roughly speaking, you need to use 3 and 4. And what comes out is precisely that these are precisely determined. And this is given by the contraction, and this is given by 0. And this shows that the bracket actually has to have that form. Okay, I'm kind of trying to wrap it up in time, which I failed. Okay. So the claim is that these axioms should show you that this thing has to look like this, and this thing is 0.
Maybe I'm getting confused, but should you also obtain that the age is closed from this?
Yeah, no, so far I haven't. Yes, because so far I didn't do the all check with all of the old. Sorry, yeah. So this thing shows us that. Okay. So if we believe in these two steps that this is one thing that you can check for exercise if you want, and this is another one. Actually, given the time in which I made this, maybe all of this is exercise. But okay, let's say this is an exercise and this is an exercise. So given these two exercises, the implication is that the bracket has to have the form that we want it to have, except we don't know anything about age, except we do, because there was a proposition we proved before, which says that this thing is a bracket if and only if age is closed. Which is the reason I arranged it in that way. And by one of the previous propositions, this thing actually has to be 0. And this was from the Jacobi identity, if you remember. And at the end. Yeah, I apologize for this little 2 insertions and maybe for going too fast. But just to repeat, the strategy of the proof was simply to first show that you can have this Lagrangian splitting, and you can use it to identify your bundle, which was abstract, with this very concrete model. And then the only thing we did was that we checked what is even the most general bracket that you can have on such a result. And it turns out that just has to be the one that we had. There is nothing else that works that would satisfy the axioms. And that's the end. Yeah, sorry for the length.
So here you have shown that the bracket has to have the form with the age, and by previously examining what the conditions for the Courant algebraic axiom.
So there was a proposition before which said that if you have a structure which is that, and this is Courant algebra if and only if age is closed.
Okay, I see.
So I'm using that to conclude.